Welcome everyone to part 2 of our 3-part series involving analysis and design of mechanical shaft systems with respect to whirling behavior. So today we're going to build on concepts that we introduced in part 1, where we talked about the basic phenomenon of shaft whirling, some simplified models, and in that part, we also talked about the mechanisms behind the shaft whirling behavior. Here in part 2, we're going to look at some analytical tools for more practical mechanical shaft assemblies, including shaft assemblies with multiple attached components. Today, we're going to go through 3 different methods. One is Rayleigh's method. Next is an approach that utilizes something called Dunkerley's equation. And then number 3 is superposition. It's actually an alternative way of using Dunkerley's equation. There are 2 main objectives today. One is to go through the practical techniques for estimating the lowest critical speed of a realistic mechanical shaft assembly. And number 2 is to gain insight in how to design shaft systems to avoid problems due to whirling and the associated vibration. Essentially, we want to learn how to design shaft systems such that we can increase the lowest critical speed such that 2 times the maximum operating speed is less than this first critical speed. Often it's not possible to reduce the maximum operating speed. In some applications, maybe it is. Maybe we can change speed ratios, we can change gear ratios to reduce this speed. But in other cases, maybe we just don't have the independent control over what the operating speed needs to be. So we'd like to increase the first critical speed so that we can avoid problems with shaft whirling. Let's have a look at a figure from your textbook. We're going to go through really the simplest possible model for shaft whirling. We're going to look at a simply supported shaft with a uniform diameter and no attached components. It's possible to derive an analytical solution for the first or lowest critical speed, and that's given in your textbook. It's equation 722. The first critical speed is going to be equal to pi over the length of the shaft times the square root of the quantity Young's modulus times the area moment of inertia divided by mass. Now, I should be clear, this is not the total mass of the shaft. This is a mass density. It's the mass per unit length. This is different from the mass that we used in part 1, where we were using lumped parameter models. So this equation is great for describing basic concepts. We can see some of the design relationships. If we increase mass, we can reduce the first critical speed, or if we increase the stiffness of the shaft, then we're going to increase the first critical speed. We want to go beyond what this model can predict so that we can actually analyze shaft systems that have multiple components attached to them. It gets a little bit more complicated. And so that's where Rayleigh's method comes in. We're going to look at equation 723. I should be clear, this is an approximation. It's helpful. It helps us to predict the first critical speed with a fairly minimal amount of calculation, but we need to keep in mind that it's an approximation. It actually tends to overestimate the first critical speed. With that in mind, it's important to use a safety factor if we use this method for estimating the first critical speed. Let's have a look at the next figure before I write out equation 723. This is an image of a similar shaft, but in this case, we're taking the shaft and dividing it spatially into discrete segments. And by creating these divisions, we can improve the accuracy of our estimate. We can also take into account varying mass. So for example, if there's a segment where we have a component attached that's heavy, like a gear or flywheel, we can take that into account when we are calculating what the overall first critical speed for this shaft system is. So with Rayleigh's method, we estimate the first critical speed to be equal to square root of this quantity, g, the gravitational constant, times a summation of the weight of the ith segment times the deflection of segment I due to the weight, divided by the summation of the weight multiplied by the deflection at segment I squared. So this index I, that corresponds to the segment number, and we're going to assume that we have n segments. So the next step requires the introduction of a new concept that some of you may have seen before, but more likely most of you have not. And this concept is of compliance influence coefficients. So a compliance influence coefficient, you can think of it as the inverse of a stiffness influence coefficient. A simple version of a stiffness influence coefficient would be a linear spring model. So, for example, if we apply a force to a linear spring, that force is going to be proportional to deflection, quantified using this stiffness influence coefficient. We can generalize this in the case of stiffness, and you may be familiar with this generalization in terms of the finite element method. So another way of writing this in the more general case involves the use of generalized coordinates. So if we have a finite element model with a number of nodes, each node has one or more different degrees of freedom that it can move, and each one of those degrees of freedom is going to be a coordinate in this equation that we're developing here. So if we have a force applied to coordinate I, that's going to be equal to the stiffness coefficient ij and multiplied by the displacement yj, so two different coordinates. We can write this in matrix form that you may be familiar with, a vector of force values. It's going to be equal to the stiffness matrix times the displacement vector. Usually the forces are known. We can derive the stiffness matrix from geometry and material properties, and usually we're solving for the displacement vector y. So this is background to introduce you to this concept of compliance influence coefficients. So I'm just labeling there, that corresponds to stiffness. But with compliance, we can define a compliance matrix that's simply the inverse of the stiffness matrix. Now, it's not always possible to invert a stiffness matrix, as you might know. If we have a singular stiffness matrix that corresponds to a system that has what we call rigid body modes, or basically it's a mechanism. There are ways that the system can move without some type of elastic resistance. So if we've defined this compliance matrix, we can rewrite the constitutive equations that we have up here using the compliance matrix. So instead we write the displacement vector is equal to the compliance matrix times the force vector. We can also write that using additional notation. So yi is equal to delta ij times fi. Now I'm using delta ij to represent the components of the compliance matrix to be consistent with the notation that's used in your textbook. So what is this delta ij? This is a compliance influence coefficient. What does it mean exactly? So delta ij is the deflection that occurs at coordinate I due to a unit load applied to coordinate j. So let's talk about what that means in terms of shaft whirling analysis. So let's suppose we have a simply supported shaft. This one I'm going to divide just into 3 segments. At the centroid of each of these segments is where we're going to consider the forces applied and also where we track the displacements. So that's where the coordinate is for each one of these segments. Suppose we have a force applied to segment 1. So if I label these segments 1, 2, and 3, and I'm interested in, well, what effect will that force on segment 1 have on segment 3's deflection, or y3? I can quantify that using this equation. Y3 is equal to delta 3, 1 times F1. So this influence coefficient allows us to take the radial force that's applied at segment 1 and calculate what is the displacement at coordinate 3. So for simple cases, such as this simply supported beam, we can use beam equations to derive what the influence coefficients are. There are other cases, for example, if we have a shaft with multiple different diameters, a varying diameter, that's more complicated, so we may need to use numerical methods to derive what these influence coefficients are. So for example, you could apply a unit load at a point to a finite element model and measure what the displacement is at various different segments. This would be a numerical approach to determine what the stiffness coefficients are. All right, let's have a look at figure 713 to give an example of quantifying these influence coefficients. So it's a simply supported shaft, and we're interested in applying a unit load somewhere along the length of the shaft. And here, just paying attention to the notation, the length of the shaft is L. The distance between the unit load and the left bearing, that's A sub j. And the distance between the unit load and the right bearing, that's going to be B sub j. And then the position we're interested in measuring the deflection at is going to be quantified using x sub I. So if we go to table A9 in your textbook, case 6, we can use the formulas for deflection described in that table to determine what the influence coefficients are. Equation 724 describes what these influence coefficients are, and it depends on whether the deflection we're measuring is to the left of the load or to the right of the load. So delta ij, that's going to be equal to bj, so remember that's the distance from the load to the right-hand bearing, times xi over 6 EIL times L squared minus bj squared minus xi squared if xi is less than aj. Or in other words, if the displacement we're interested in is to the left of the applied load. So that's one case. And I should point out, at least in the 9th edition of the textbook, there is a small typo. This should be AJ, not AI. In the 9th edition of the textbook, it says AI. So what if the displacement we're interested in is on the right-hand side, or in other words, xi is greater than aj? Then the formula, based on the beam formulas from the appendix, is going to be equal to aj times L minus xi over 6 EIL times 2L xi minus aj squared minus xi squared. So this is a really simple case. You can use superposition and beam formulas that you can look up to really derive what the influence coefficients are for a wide variety of different situations. It's certainly a lot easier if you have a uniform diameter shaft. So looking at this with influence coefficients, suppose if we have this case where we have 3 different segments, n equals 3, the number of different influence coefficients then is going to be 9, or 3 times 3 is equal to 9. That's the number of elements that are going to be in this compliance matrix C. Now, there's something known as Maxwell's reciprocity theorem. And it essentially says that the compliance matrix is symmetric. Or, in other words, we can write that delta ij is equal to delta ji. So what does that mean? That means if we have a load, say at j, and we measure the deflection at I, that influence coefficient is going to be exactly the same as the opposite situation if we have a load at I and we want to measure the deflection at j. Another important outcome of this is it reduces the number of coefficients that we need to derive. So if we had a n equals 3 system, instead of 9 unique values that we need to derive, we only have 6 unique values. So there are a number of different types of loads that are relevant to shafts. One is weight, W sub I. I'm going to try to do my best to write that differently than omega, which we use pretty extensively in these equations. And then another important type of load involves inertial forces due to centripetal acceleration. And so those forces, say for a single segment on the shaft, is going to be equal to the mass of that segment times the rotational velocity times the transverse deflection of that segment. Now we can take these and now write a system of equations where the deflections at each of those segments are going to be equal to the compliance matrix times a force vector, and then this force vector, if we're neglecting gravity and it's only due to the inertial forces, that's going to be equal to m1, y1, m2, y2, m3, y3 for this n equals 3 case, all times omega squared. Now in part 1, I mentioned that there's an associated eigen-problem with critical speeds for whirling vibration of shafts. And this equation that I just described, y equals c times f, it's this system of equations that results in the associated eigen-problem. And what we're going to talk about next is a way that we can identify the critical speeds with respect to whirling for the system. So if we have n different segments in the shaft, then we're going to have n critical speeds. But really, we only care about the first one, the lowest speed. We need to make sure that we are rotating at least half as fast as this lowest speed, or we want to be below 1/2 of this first critical speed. So how do we go about doing this? We can rewrite this equation, first of all. Set that equal to 0. And it's possible to define a matrix such that this system of equations is equivalent to a system that looks like this. So there's this matrix that we need to define A minus a vector, lambda, times the identity matrix, and that's equal to 0. So this vector we're going to define as one where each element, the ith element of that vector, is equal to 1 over the square of the ith critical speed. It's possible to derive this matrix, and in your textbook it goes through a simple n equals 3 system that it works out the equations for this. But it's possible to simply write out this matrix using this formula. So the matrix is going to be equal to the compliance matrix multiplied using the Hadamard product times a mass vector. So I need to define what I mean here. So this mass vector, at least the way I've written this equation, that's going to be a row vector, m1, m2, so on, all the way up to mn for the nth segment. And what is the Hadamard product? It's an element-wise multiplication. If you are familiar with MATLAB, that is simply going to be equivalent to the dot times operator. So what would an element-wise multiplication look like? If we had a vector a1, a2, and we wanted to do a multiplication of that, say b1, b2, instead of coming up with a scalar, it would result in a vector. So we would multiply and we get A1, B1, and A2, B2 as the result of that. So you might want to both look up the Hadamard product and also look at the dot times operator in MATLAB to learn a little bit more about how this formula works. It's a fairly simple way of deriving this matrix. So now we have this equation defined. What are we going to do with it? It probably looks familiar to you if you're thinking back to your differential equations class, and especially if you've had a class on linear algebra. This is partway through the technique needed to derive the eigenvalues for a matrix. So if we derive this and take its determinant, I'm going to drop the square brackets for convenience here. A minus lambda times I, set that determinant equal to 0. This gives us what we call the characteristic equation. And we want to find the roots of this equation such that this is satisfied. And the roots are going to be the eigenvalues. And in our case, each of the eigenvalues, they're going to be 1 over the corresponding critical speed squared. Okay, let's move on to equation 729. It's possible to show if we sum all of these eigenvalues, that's going to be equal to the sum of all of the masses times all of the diagonal compliance influence coefficients. So remember what the main objective is here. We're trying to estimate what the first critical speed is. And to do that, we can make a few assumptions. I'm going to define a term here. What happens if we have a single mass acting alone? What would the critical speed be for an n-segment shaft if only mi was contributing? With this question, I can define then a quantity, omega ii squared. That is going to be the critical speed of an n-segment shaft if only mass I was contributing to it. And we can write that this is equal to mi times delta ii. So now let's take this equation 729 and look at the right-hand side. Oh, well, that corresponds to this right here. Let's do a substitution. Let's substitute this new quantity, the critical speed with respect to mass I, for the terms in this summation. So if we rewrite that, we can get and this is equation 730. Now, this is a nice relationship, but if we go back to this main objective of only needing to figure out what is the first critical speed, this actually becomes really useful. We can make an assumption that if we have ordered all of the critical speeds such that omega 1 is the smallest critical speed. And with that assumption, if there's enough space between these critical speeds, then we can say that 1 over omega 1 squared is going to be significantly larger than 1 over omega 2 squared, and so on. Now, we can think of these as higher order terms. And if we look back at this summation, it's really the first term that makes the most significant contribution. So if we neglect all of the higher order terms, we can arrive at this approximation. 1 over omega 1 squared, ignoring all the higher order terms. And that's going to be equal to the same summation from I equals 1 to n of 1 over omega II squared. And I should emphasize this is an approximation, sort of like Rayleigh's method. It's an approximation. There are a number of advantages to this. It's easier to calculate what we need for this. So we only need the diagonal influence coefficients so that we can get all of these terms, and then we can solve for the first natural frequency. This equation is what's known as Dunkerley's equation. This equation is conservative. In other words, it underestimates the first natural frequency. Okay, we're moving on to the last topic we're going to cover in this video segment. We're going to look at this concept of using superposition in combination with Dunkerley's equation. As with other ways of using superposition, it's only valid for small deflections, so keep that in mind. One of the important things to observe is Dunkerley's equation, just going back to this equation from the previous page, it does not involve any of the loads directly. And with that observation, we could use what we call an equivalent load that we define at a convenient location. And what I mean by equivalent load is we can choose a location that's convenient. For example, maybe the center of a shaft is a convenient location. So say we have a force acting at the center. But what if the original force was acting at some other location, and we are interested in the deflection at another location, yj? So we can derive for a simply supported beam what's the influence coefficient that's going to relate Fi to yj. But can we come up with a force that is applied at the center that will produce the exact same deflection at location j that Fi would have produced if it was applied at location I? Okay, so how do we go about using this observation? Now remember, this is the square of the critical speed due just to mass 1. And we can write from equation 729 that this is equal to 1 over m1 times delta 11. We can make a further observation that m1 is going to be equal to the weight at 1 divided by the gravitational constant. And so I can write this is going to be equal to g over w1 times delta 11. Now, to define a way of quantifying equivalent load, I'm using this example. I can write G divided by this equivalent load W1C. So this is the load that would need to be applied at C to produce a deflection at another location that's equivalent to the deflection caused by W1. And this is multiplied by the influence coefficient defined at the center. So now with this setup, we can actually solve for this equivalent load. That's going to be W1 times delta 11 over delta CC. And both of these influence coefficients are easily derived using beam equations for our simply supported shaft case. And so now everything on the right-hand side is known, so we can calculate what the equivalent load is. So the next question is, how can we use this with Dunkerley's equation? So recall Dunkerley's equation, 1 over omega 1 squared is going to be equal to the summation 1 over omega I squared. We can rewrite that 1 over omega 1, that's equal to the square root of 1 over the summation of 1 over omega I squared. And from above, up here, we can write that omega I squared is going to be equal to G over W IC times delta CC. So I basically took this and generalized it for location I instead of just location 1. And then if I substitute this in here, and then we do some algebra, which I'm going to skip, the result is omega 1 is equal to the square root of G over delta CC times the summation of WIC. So this is an alternative way of using Dunkerley's equation. This is going to be used in the next example. And so I just wanted to lay it out a little bit more clearly than it might be in the textbook, fill in some gaps. So we're going to wrap this up, and I'm just going to point out in part 3, we're going to work through the example 7.5 from your textbook, go through that in a little bit of detail, and then I hope everyone will be well prepared for the homework and the upcoming exam. Thanks.